Hello again, physics friends. We have seen that the work kinetic energy theorem relies on us calculating a quantity that we called work, which was defined to be an integral from one position to another of a force dotted into a small displacement dr. This quantity on the right-hand side we call a line integral or a path integral because they're integrating the force along a path, and we need to know the path that's taken. So we call this a line or path integral. And it takes some practice to learn how to actually calculate this line or path integral out appropriately. So that's what we're going to focus on today. We're going to do a few examples where we are given a force and we are given a path and we have to compute the work done by that force on that path. Sometimes the work done will depend on the specific path taken. Sometimes it will not. Okay, so let's see, and then we're going to try to understand, like, what does it take for a path, so for a force to be conservative? In other words, the work will not depend on the path, versus a force that's non-conservative, in which case the work does depend on the path. Okay, so let's play this out. Let's start with a specific example, and let's have this example provide us with a specific force, and that force is only dependent on the y coordinate, and it only has an x component. And we're going to think about two paths, and we'll compute the work done by this force on two different paths. Okay, but first of all, what does this force look like? If we were to draw force vectors at different positions, what would they look like? Okay, so I'll start by drawing it out. We have our x and y coordinates, okay, and notice that I'll draw in purple the force vector field. Notice that my force never has a y component. So all of my force vectors are going to point in the horizontal direction. And notice that the length of my force vectors depend only on the height, y. Okay. So all along the x-axis, I have no force because I'm at y equals 0. Okay. So the length of my force vector is 0. As I go up, now I'm going to have a force vector that is pointing to the right. And every one of these force vectors at this height is the same length because I'm at the same y coordinate. As I go higher, my force arrows get longer. And so on. Like that. Okay? And let's consider the case where we have a starting point, let's say at the origin, and we have another point over here at 1, 1, and I'll call that point P. Okay, so my path in this example will always start at the origin and ends at P. But we could get there in different ways, and we're going to look at two examples. Path 1 is we're going to go from O to P via point A. Point A is 1, 0. So path 1 is origin to A to P in straight line segments. And then in part B, we'll take path 2, which is O to P, but we're going to get there via point B, which is at coordinates 0, 1. All right. And that is the game. So we're going to do two different path integrals. And we're going to see, what we're going to find is that the work done by this force is different for the two paths. So let's see why that is. First, via path A, or via path 1. Okay. So that's starting at 0, 0, going to 0.10, and going from there to 0.11. All right, so let me draw that in red. So that's my red path, okay? So what is the work done along path 1? Okay, well, we have the work done by this force from the origin to A plus the work done from A to point P. Okay, so let's write this all out. The work done by going from the origin to A is going to be really straightforward because the force on that leg is 0. Right, so it's the integral of f dotted into dr, but f equals 0 everywhere on that path. So there's no work done in that first leg. Okay. How about the work done as we go from A to P? That's going to be the integral of f dotted into dr along that path. But notice something about the dr, which is a little leg, a little segment along that path. That's always in the y direction, and the force always points in the x direction. So those two are perpendicular to each other, and that force is also going to be 0. And this time it's 0 because everywhere along this path, f is perpendicular to dr, so the dot product is 0. And we can be even more specific about that, just more explicit rather about that. So in this case we have, we could write the force as y comma 0, that's what it is. We can write the dr vector as nothing in the x direction and dy in the y direction. And when I take that dot product, I get y times 0 plus 0 times dy. So that tells me that I have 0 as my integrand. And so the overall work along that leg is also 0, and we have the result that this force does no work as the particle goes from O to P via point A. So we're done with part A of this problem. We're going to see that via path 2, the work done is non-zero. So let's find out what it is. So our second path is, I'll draw in green. We start at the origin, we get to point B, and then we go from point B to point P. So there we go. And we can write the work out in two ways. The first element is the work done in the vertical part, and the second is the work done in the horizontal part of our path. The work from 0 to B is going to be 0 for the same reason that the work from A to P was 0. The path is perpendicular to the force. Okay, same argument as before. But now, up here, as we go from B to P, we see that the path is going to be parallel to the force, number 1, and number 2, the force is not 0, like it was down here. So we are going to get a non-zero work done by this force. So this is where we have to write everything out explicitly. Okay. For this part of the problem, WBP, we have the following. We have the force out, well, here the force everywhere is y comma 0, but for the path B to P, the path dr is a step in the x direction and no step in the y direction, so that when we take that dot product of f dot dr, we get y times dx. Okay, but specifically along this path, the path B to P, we have specifically y equals 1, don't we? Because we're up at a coordinate of 1. So that tells us that f dot dr is equal to 1 times dx, or just dx. And so this integral the integral of dx, or specifically, I guess, let me write it out. It's the integral of f dot dr from r naught to rf, or r initial to rf, but we showed that f dot dr on this path is simply dx, and we're starting at x equals 0, and we're ending at x equals 1, and when we do this integral out, we get 1. So this tells us that the work done along path 2 is simply 1 unit, 1 joule. The unit of energy here is the joule. A force has units of force times distance. Okay, so we have the interesting result that we've computed the work 2 ways and it's not equal. Okay, so the work depends on path. So we say that this force is not conservative. Not conservative means you cannot say, I have a particle at point P, I know its energy, because if it got there via point B, it will have a different energy than if it got there via point A. So if the energy of the particle depends on how it got there, the associated force is not conservative, and what we'll see is that means that the mechanical energy there's no associated potential energy for this force. Okay, so we're going to come back and identify forces, find ways to identify if a force is conservative or not. And if it's conservative, we'll define an associated potential energy. Okay, so we've done one example here 2 ways. I want to do one more example. So this next example will use a different force function. This force function will be representative of what I'll call the 3D harmonic oscillator. So imagine a spring that's pivoted, that's fixed at one point, but the other end of the spring is allowed to move anywhere in space. And if that's true, not just in the 1 dimension, not just in 2 dimensions, but in 3 dimensions, and if that's true, then the restoring force associated with that spring will always point to the origin minus r hat, and the force will be proportional to the distance from the origin. So we can draw this force field out in the following way, and I'm just going to draw it in 2 dimensions. Right. So the idea here is the further you are from the origin, the longer the force is, and the direction that the force points is always to the origin. So you end up with a force field that kind of looks like this. It points radially inward everywhere you are, and the length of the associated force grows as you move away from the origin. Like so. So we're going to consider this force, and we're going to move on 3 paths. And we're going to compute the work done along those 3 paths. All of these paths are going to start at 1, 0, and they're all going to end at 0, 1. Okay. So we'll start at 1, 0, and we're going to end at 0, 1. But we're going to get there 3 different ways. Path 1, it's going to be 2 line segments. So we're going to go from the starting point to the origin, and then from the origin up to the ending point. Path 2 will be a circular arc, and that circular arc will trace out a path like so. Okay, and then path 3 will be a parabolic path. X equals 1 minus y squared. So let me first just draw each of these paths. We'll have a red path, that's the first path. In green, I'll draw the circular path, like so. And then in, how about in orange, I'll draw my parabolic path, like so. Okay, so those are our three paths. Notice that the path 2 and 3 are quite close to each other, but they're not the same. What we're going to find is that no matter what path you take, we're going to find that the work is 0. And so that's suggestive that the work is path independent. We're taking 3 different paths, we get the same work. It doesn't say for sure it's path independent because we haven't tried all of the infinite number of paths, but we will find a way to determine definitively that this is indeed a conservative force. But let's start. We'll start with path 1. And the work on path 1 is given by the work from A to the origin plus the work from the origin to B. So we can label that in the following way: A to origin, origin to B. And we can see just strictly from symmetry that those two works are going to be equal and opposite. Okay. How do we see that so quickly from symmetry? Well, we have a path that is parallel to a force in the same direction of the force, right? When we go from A to origin, and then we get to the origin, we go up to B, and we have the same length path and the same set of force vectors, but now our path is pointing opposite the force. So in the first leg, we have a positive work done. In the second leg, we're going to have a negative work done, but the magnitude of those two works is going to be the same, so they're going to cancel, and we'll be left with 0 force. But let's actually do this out. Let's do this out explicitly. So WAO, this is the first leg. We have a force vector that is equal to minus k times x, y, z. We're always going to be at y and z equals 0. So our force vector is minus k 1, 0, 0. Excuse me, that's x 0, 0. And our displacement vector dr is dx 0, 0. On this path, we are only moving in the x direction. We have no motion in the y or z direction. Now, you might wonder why it's not minus dx. Well, dx is a quantity that could be negative. And in particular, in this case, it is. It does point to the left, starting at x equals 1, ending at x equals 0, but we just represent it as dx. And the limits of integration will take care of the direction. Okay, so we can then take the dot product f dot dr, which is mostly zeros, except we have from the x components minus k x dx, the rest is zeros. So when we talk about the work going from A to 0, we have the integral f dot dr evaluated at some limits that we'll put in a second. That gives us the integral of minus kx dx from x equals 1 to x equals 0. And if we evaluate that out, we have minus 1/2 kx squared evaluated at those limits. Okay, so that's minus k over 2, and when we evaluated the limits, we get 0 minus 1. So we have a work of 1/2 k for the first leg. Okay, you can do the same thing for the second leg, and you're going to find a similar response. Let's just do that explicitly here. So leg 2, that's the work going from the origin to point B. And in that case, our force is minus k, and then we're at the location x equals 0, z equals 0, but we're at a y coordinate that evolves. Our position step dr is nothing in the x direction or z, but we have a step in the y direction. So f dot dr in this case will be minus ky dy. And so the work on this leg is equal to the integral f dot dr which is integral minus k y dy from y equals 0 to 1. And when you play that out, you get minus 1/2 k for the work. So when you add these two together, you're going to get a total work of 0. Okay, so it's not that the work done is 0 for each leg. We have non-zero work on each leg, but they're equal and opposite quantities that sum to 0. For path 2, we're going to very quickly see that the work must be 0 via path 2. And the reason that the work must be 0 is that as you march from A to B along the green path, everywhere along that path, the force is going to be perpendicular to the path. Okay, so we can see that that's got to be true. Here we have the force everywhere is perpendicular to dr along path 2. Why is that? Well, the force is radial, and dr is tangent to the curve, and the radial and tangential directions on a circle are perpendicular. So if that's the case, then f dot dr is everywhere 0. So when you integrate f dot dr, you're going to get the integral of 0, and you get 0. So we found on path 1 the work is 0, and here we quickly can see also on path 2 that work is 0. So what's left then is to look at path 3. So along path 3, we have a force that's equal to minus k x y 0, and we have to have both x and y present because we're on path 3, we're experiencing forces that point in the x and y direction, not just in the x or the y directions individually. And our vector dr is going to be dx comma dy. We need to keep both of those components because our path has components in both the x and y directions. But how can we express this only in terms of one variable or the other? Well, for that, we're going to make use of the specific path that we take, right? So out of that expression, we can relate dx and dy. So if we take a derivative of this, we find that a step in dx is related to a step in dy in the following way, minus 2 dy. So for if we step in the x direction, we have to step twice as far in the y direction. Every step we take in x, we step twice as far in y. And if we take a step towards the origin in x, we take a step away from the origin in y. That's what the minus sign says. So now we can actually express our dr vector in terms of one variable, minus 2y dy, comma dy, or equivalently, minus 2y comma 1 times dy. So when we take the dot product of f and dr, okay, we'll get a minus kx times minus 2y. And to that we add a minus ky times 1 all times dy. And here we can replace x with this expression 1 minus y squared. So we get minus k 1 minus y squared minus 2y dy. And then the second term is minus ky dy. Okay, so we can expand all of this out. We get plus 2 ky dy minus 2 ky cubed dy minus ky dy. Okay, which gives us, at the end of the day, 1 ky dy minus 2 ky cubed dy. That is the dot product of f and dr. So now we have to integrate that to find the work. So we march along here and we say that the work done along path 3 is simply the integral of this whole thing that we just found, ky minus 2ky cubed all dy, and we're integrating that from y equals 0 to y equals 1. Okay, well this integral is straightforward. The first term is k over 2y squared. The second term will be minus k over 2 y to the 4th. And we're evaluating this at the limits 0 and 1. So we'll get a k over 2 minus a k over 2 from the y equals 1 term, and we get a 0 minus 0 from the y equals 0 term, and notice we end up with no work as well along the orange path. So we've now computed the work done in going from A to B along the red, the green, and the orange paths, and in every single case we found 0 work is done. So that's kind of suggestive. And you might wonder, is the work in going from A to B equals 0 on any path? Okay, and it turns out that yes, it is. But rather than doing this calculation for the infinite number of possible paths, there must be a better way. And what we'll show in the future is the tool that we can use to determine if work is path dependent. And we're going to learn that if the curl of the force is 0, then we can make a statement that the work is path dependent. And in that case, like this one, where the work is path dependent, we can say that the force is conservative. And that there's an associated potential. Such that the force can be written as the gradient of a potential with a minus sign. So those are all previews of things to come. We'll get there eventually, but for now, take care and be well.